So welcome to the second lecture for network coding. What we saw last time is really the introduction to network coding by the example of digital interflow network coding. And today I would just like to go a little bit back where we have been last time with the cross, repeat the cross a little bit, and then go to the analog digital interflow network coding. So what you have seen last time is the so-called butterfly example with some specific use cases, explaining you how you should code and where you code with deterministic codes, as well as maybe the outlook for random codes later. So what we start last time was really this cross topology where we had Alice and Dave, Charlie and Bob. They would like to communicate over a relay. And in case of pure relaying, so when there's no network coding, if they want to exchange packet with each other, you see even that in the case that there's not so much load in the system, the Alice will send to the relay, then Bob will send to the relay, Charlie will send to the relay, Dave will send to the relay, and then the relay will send out to the counterparts, right? So as you can see here, you need 8 time slots, and everything is fine as long as there's not enough capacity. And what you see later is, in the second example, what happens if there's not enough capacity. And as you have seen in the example with Alice and Bob, all the devices in a Wi-Fi testbed, they will always get the same capacity. So if you really have only one slot to send, what you see is if there's a lot of load towards the relay, all of them send to the relay, and then the relay can only choose one, either A, B, C, or D. We choose A here, but it doesn't matter which it is. And it's not very efficient, right? Only 25% of the communication is successful in this case. And then last time we already discussed it, that with network coding, there are 2 ways of network coding. One is network coding between the flow of A and D, which would be the XOR network coding. Now we are just saying, okay, instead, when we fill up the relay, sending always Alice, Bob, Charlie, and Dave to the relay, then the relay only needs to send twice in the case that there's not enough load in the system. So Alice and Dave send there, then you XOR it and broadcast it out. The same for Charlie and Bob. You send it to the relay, XOR and send it out. So with only 6 compared to the 8 that you had before, time slots, you can make the full exchange. But even here, if the load increases, all the devices will get the same sending slots. And also here you only have 1 slot where the relay can send, but in this case of only making 1 happy, you make 2 happy, right? In this case it's Alice and Dave, but it could be also Bob and Charlie, doesn't matter. So now you make 50% happy. The other thing with network coding is that you don't have to do it only between the flows between them. You can even go over all flows. This is XOR network coding with overhearing. Now we say, okay, the relay, we send to the relay, and all the nodes will overhear the other side. And with that, you will understand that after the first sending phase, you see how many receiving slots you have compared to before, where you have a lot of idle slots. And now you have a lot of receiving because the overhearing takes place in all of the directions. When C is sending, you see it here, only Bob is idle, the one that really wants like to have it, but he's idle. The others will overhear it or receive it directly, so that in the end, the relay only needs to XOR all the incoming packets only once. And now it doesn't matter if there's high load or low load, you always have the best possible connection. And what we saw last time is the throughput over the total load, and you see for all the 3 cases, the load will increase until with 50%, where 50% from the outside comes in, then the throughput will decrease again until we all have the same amount of sending, and then you end up in 20% efficiency. Now later you see that for the XOR over the flows, you can see that you increase the throughput a little bit, but also here you decrease until you stabilize it with 80% coming from the outside at 40% throughput. only the XOR with overhearing, what you see is you go up to 80% and then you stay stable here because you only have this kind of pattern. So what I mapped to you here is the high load scenario for the different things, XOR with overhearing, just XOR, pure relaying, and then you see here the XOR and the pure relaying in the low case, right? Because this is also true for the others here. Now, we stopped when we said, okay, why is it really going down, right? You could easily also say, we could identify this point in time and just stop over here and say, why going down? Once the incoming nodes understand that they are doing only bad for themselves, you could stop them. It's very hard with Wi-Fi drivers, but if you have your own hardware under control, which we had, we have here a hardware with a 16-bit PIC24 microprocessor with an NRF 905 transmitter, 433 megahertz with 50 kilobit per second, very low data rate, but it doesn't matter. We just want to understand the access to the wireless channel. We had our own MAC protocol. It's a CSMA-CA design like Wi-Fi. And now we had our own network coding, a simple XOR design, right, which was close to what MIT did with XOR in the air. And then our capability here was that easy access to the software and full control from hardware and software design. I think that is quite interesting. And when you did then the measurements, here you see the throughput and the total offered load for the standard one and the XOR over the flow, not with the overhearing yet. And you see we could stop at this certain points. This is the model, the expected one. And here are the measurements. And when you look carefully, here you still see that you dip a little bit, the same here. And this is due to the fact that we have seen also with the Catwoman approach, where we had buffer bloats, where the queues really, there's something with the queue management here that worked. And the way how we stabilized it at this point was just with MAC priorities, saying the relay has more priorities than others. So you could imagine when you have Wi-Fi with a backoff window, you just give those devices a better access to the channel when and only when they have more coded packets. So if you have a normal packet, you stand to the backoff window. But if you have two packets coded together, you halven your window. That could be a very simple rule for that.